Welcome everybody. First quick question. Who here doesn't speak any English? Ki nem beszél angolul? I'm sorry you have to leave now. Okay, that's useful. Especially useful because we only have one Hungarian speaking presenter today. So three of the Hungarian speaking, three of the presenters, all three of the presenters will be speaking English for Meetups. So welcome. This is the Mozilla Developer Roadshow edition of our Rust Hungary Meetup. This is the second ever Rust Hungary Meetup. Who was here for the first meetup? Anybody? Oh, we had a few people. All right, welcome back, and welcome our newcomers. I hope you're going to enjoy this. Sorry for the technical difficulties. We're still getting into all the technical stuff. Some of the equipment is new, so excuse us for all the technical hiccups. We're gonna record all the presentations and we're gonna upload them online as soon as we're finished post-processing them. This goes for the first meetup, so if you were the ones raising your hand just now, were the ones that missed the first meetup, you can still catch some of the great talks. We actually have the University of second team here who's returning for a second time, so you could check back on the first version of their the first talk from last month. So welcome everybody. I'm István Smorzsászky, or short for Flaki. I'm part of the local Mozilla Hungary team, and we are the ones helping you, bringing you the Rust and Rust Hungary meetups to Hungary, and also a bunch of, you might have met us in a bunch of meetups around Budapest mainly. So just a word for our sponsor. Today's Mozilla Developer Roadshow event is brought to you by Mozilla. And if you want to help them, there's a survey link, mzl.la/devsurvey. You can contribute to, have Mozilla, make Mozilla better understand you, or your needs and your wants. So feel free to go there and fill it out. So Mozilla, who here? So Mozilla is a non-profit company. Who here didn't know that Mozilla was a non-profit? Anybody know? All right. So Mozilla is a non-profit company created maybe 50 years ago. When Netscape went out of, when the Netscape browser's source code was open source. And most of the people still know Mozilla about their open source browser that they created right afterwards, which is Firefox. There's a nice graphics right beside me about the new things, which kind of conveys the new things and the stuff that is coming in the upcoming version of Firefox, the Firefox Quantum edition, but I'm not going to steal the wind out of Nicolas and all the speakers' sales. So you will hear a lot more about Firefox today, I also want to remind you that our event has a code of conduct, which the short version of which is, please try to be awesome to each other. We're gonna have, in the breaks and during the meetup, and we're gonna have an after meetup thing. We're gonna visit the CSSConf pre-party right after the meetup ends. So all of this are covered by the code of conduct. So please try to be awesome to each other and see the link for further information about the code of conduct and how you should behave besides being awesome. Enjoy. There is a bunch of things that you're going to hear about today, including Rust and a bunch of the stuff that is coming into Firefox. The project Quantum. You will hear a lot about these things today, but at the end of today we're going to have an announcement So you will be able to hear a lot more about more Rusty things in the coming months. Who here is here for CSSConf or JSConf? A bunch of people. Well, we managed to do a pre-JSConf meetup, I guess. So if you're going to be around at JSConf, we're going to have a Mozilla Hacker Lounge where we still, eagerly await your lightning talks, where you can give a lightning talk in 7 minutes in the morning coffee breaks, but also noon and in the afternoon you're going to get even more talks during the lunch breaks, some discussions with speakers, and more importantly, you will be able to try some of the web Bluetooth stuff the second team was hacking on. And if you have been here for the first meetup, you might have seen the RC controlled cars and all the other cool gadgets that they are controlling with web technology. So feel free to drop by the Mozilla Hacker Lounge and play with all these things if you are at the conference. Besides that, we wish you a very good conference. We hope you're going to have a great time at the conference and outside of the conference in Budapest. Let me just quickly skip that. Yeah, we also want you to get involved. So as I mentioned, Mozilla is completely open source. So a bunch of the projects you will find on GitHub already. You might have not known, Google Chrome got very, most of his famous lock-in to the browser from its great developer tools. And you might not know, but so the very first developer tool in the browsers was Firefox, which is being phased out as Mozilla switches to an built-in browser DevTools. And the Firefox DevTools that are built into the browser are actually made with pure CSS and JavaScript and HTML5. Pure as in, it even includes React. And the whole thing is on GitHub, so you can contribute on GitHub to the Firefox developer tools with JavaScript skills, which is pretty cool, I think. But Mozilla has a bunch of other projects that you can contribute to if you feel so. So please do, and feel free to talk to us. There are a bunch of Mozilla folks, contributors here, who can answer your questions if you have any of those. So we are going to take it away. As you have seen, we're going to have 3 speakers today. The first speaker is going to be Nicolas Silva, talking to us about Firefox Quantum and WebRender, and a bunch of other things he does in Mozilla in the Paris office. He's a graphics engineer on the Firefox team. So Nicolas, please take it away. We're going to have a short slide switch and setup, and we're going to kick it off in 1 second.
We're good? Good. Excellent. So hi everyone, I'm Nicolas. I work from the Paris office as a graphics engineer on Gecko, and lately on WebRender, which is written in Rust. I didn't realize this was a Rust meetup, so I should highlight that because I love Rust. At Mozilla, we've always, for as long as I've been here at least, so like for a bit more than 5 years, there's always been this thing where we have this big project that is a really ballsy cross-team effort with some risks, and it's always been something that I find amazing because in a lot of companies we try to avoid risks. And we'll try to, incrementally do some things. And at Mozilla, there's always been this one project that drives the engineering workforce forward and does a lot of very coordinated cross-team efforts and things like that. And a lot of the stuff that I'm going to present today would not be possible if we didn't have the courage to sometimes take some risks and just focus a lot of our engineering into very, very dangerous projects. So when I arrived, we were porting Firefox to Android, and that's quite a feat when you think about how a browser is made and how much work would go into porting it to such a different architecture and platform. There's been the Firefox OS project. There's been Electrolysis, the multi-process Firefox. You've probably heard about it. Those are a lot of these things are things that may not have paid off. For instance, Firefox OS didn't succeed so well, but it was clearly a pretty impressive technical feat. If you didn't know, Firefox OS could run you could watch Facebook on a $20 smartphone using Firefox OS, and I know what hardware was in there, and I still can't believe we managed to do that. Android was not able to do that back then, and I don't know if they can do that now. So I'm going to talk a little bit about Quantum, but really I'm mostly going to talk about the stuff that I work on, which is the Quantum Render. But let's mention the other ones because they're exciting as well. There's the Quantum Flow effort, which is basically a cross-team effort where a lot of people gather, they look at profiling data and start asking the painful question of why this thing is slow, or why is Chrome faster than Firefox on this thing, or why are we doing so bad on that particular benchmark. And it looks like something that we should always be doing, and it's actually something that we're always doing. But with the Quantum Flow project, we really took a lot of people from a lot of different teams, and we put them together, and we managed to actually move a lot faster on these things and do some bigger moves than we would if there was just like a handful of people in a handful of teams not talking to one another, working on profiling and such. The Stilo project is quite exciting for the Rust lovers like you and I. It's pretty much, like you probably heard about it ad nauseum by now, so I'm just gonna skip over it. But we took the style system from Servo and we put it in Firefox, and it's really fast. For some pages are actually like something like half a second faster to start up, which is enormous. For at least for someone like me who works on with like a frame budget of like 15 milliseconds, so half a second is like eternity. Quantum DOM is also quite interesting because it tries to minimize the effect that background tabs have on your browsing experience. So we took all of these JavaScript contexts and put them into different event loops. Before that, they were all of the JavaScript contexts on one given content process would just run on the same event loop. And every now and then, this background tab would do something really nasty and schedule stuff in your event loop, and then you'd be stuck doing JavaScript work for that tab that you're not even looking at. And so the Quantum DOM project is really aimed at making sure that we can not schedule that work. If there's work to do on the tab that you're currently looking at, and some other tab tries to add work, we're always going to do that thing that you are looking at first, because this is what needs to be responsive and such. The Quantum Compositor, I'm not sure I should really put that in the Quantum sort of list, but it was labeled as a Quantum project. It was actually planned and almost ready before we even started thinking about Quantum. So, but it's there, and it's quite nice. We moved a lot of the stuff that we do on the GPU into a separate process that we call the GPU process for obvious reasons. And that brought a lot of stability to Firefox, like a lot less crashes with the GPU process on Windows. This is because drivers are really, really buggy, and they're buggy in very different ways. Like every one has its own like setup with its own configuration, and everything blows up somewhere, but in very creative and different ways. So we can't really trust GPU drivers. This is the thing we learned the hard way. And now we sandbox it into a process that if that process crashes, we can just stand it up again and not have to reboot the entire browser, which is pretty sad for the user. There is the Quantum Render stuff that I'm going to talk about in a minute. This is pretty much integrating WebRender into Firefox. And there's Photon, which is the idea of that all of these great things should come with a visible UI change as well. And so we made the tabs more square and prettier and more designed, etc., etc. And also, it's also part of the Photon project was also to make sure that we had more snappy animations in the way you interact with the browser, so that it feels even faster in the way, like in the motion design and things like that. Now, let's get into Quantum Render, the stuff I work on, stuff that gets me excited. But before I get into that, it's really hard to present the Quantum Render stuff without first going into a little bit of an overview of how all web browsers work today. So I suppose that you guys all know about the DOM tree. This is what you interact with in JavaScript, and this is pretty abstract. It's like you have divs, you have nodes, and they're not really positioned in space. You have some text right there, and then an image next to it, and then something snapped to the right of something else. And we don't really have the positions of these things. So what we do in the browser is we compute the layout of the page, and we build what we call a frame tree in Firefox, which is also named a flow tree in Chromium, but it's basically the same thing. And it contains the information of the positions and sizes of everything. From that, we build a display list, which is pretty much a list or a vector of drawing commands that need to be painted, but we still haven't drawn anything at this point yet. We also break web content into different layers. Layers are like those layers that you have in Photoshop or GIMP or most image editing software. They're images, you can think of them as images that are separated so that we can move them around cheaply, and then we composite them together in that final phase that we call compositing. And painting is the action of taking display items from that display list and painting them into layers, which means actually drawing some pixels. But before we can do the compositing, because now Firefox is a multi-process browser, we also have to share those layers that were drawn that were painted in the content process to the compositor process. And there's a bit of a complicated thing going on there where we want to do some form of double buffering and avoid copying data because images are big and your screen has a lot of pixels. So if we had to copy all of them through a pipe, every time we sent stuff to the compositor process, that would be pretty expensive. So this is sort of roughly how things work, and this whole design was meant to make sure that the compositor can always composite at 60 frames per second and stay smooth. And that's quite important because if you're on a phone and you're scrolling, you have your finger on your screen and you're moving your finger to scroll the web content, it's really jarring if the web content is not following your finger at 60 frames per second. So it's really important that scrolling stays smooth, and having a compositor is a pretty easy way to make sure that scrolling stays smooth. But on the other hand, every time you have to do some painting, there's this deep pipeline of things that need to happen before anything gets to the screen. So the way we go about painting is that we pretty much go through the display list from in back to front order. So say you have some text, and in the background you have a red rectangle, and then there's the white background of the page. Well, first paint the white background of the page, then the red rectangle, and then the text. It sort of makes sense, right? Because it's pretty hard to draw text and then what's beneath it because of all the anti-aliasing, and you would need to make sure that you're not overwriting and stuff. So it's pretty natural, and it works pretty well on the CPU because the CPU it's doing an okay job. Like, it's fairly good at switching back and forth between different things. Sure, if you have a hot loop and you're switching between different kinds of things in that hot loop, you're going to have really bad cache performance, like instruction cache performance, and even maybe data cache. But in our case, our hot loop is this loop that goes through every pixel and paints them in your primitive that paints rectangles. And so it's fairly okay to say, okay, let's paint a rectangle there, an image here, and then another rectangle here, some text, and go through things individually and paint them. And we do that with an abstraction that is fairly similar to Skia or Caro or Canvas 2D, like immediate mode drawing APIs, if you're familiar with any of them, or at least one of them. Who's not heard about Canvas 2D web? Raise your hand. Okay, so most of you know about this kind of stuff, right? The thing is, we want to use the GPU for painting. Screen resolutions grew, and CPUs are not the best at filling a 4K screen 60 frames per second. And so we want to use the GPU because the GPU has been built exactly to do that. The problem is the programming model on a GPU is very different. You really don't want to go, oh, draw some text there, draw some rectangle here, draw some image here, and then another rectangle, and then another image. What the GPU likes is when you give it a batch of many of the same thing, and then another big batch of many of the same thing, etc., etc. Basically, you have the way you program your GPU is to set a shader program, and you say, oh, okay, here's the current shader program. That's the one we use to draw, say, images, and then we set this mode, and then draw a lot of things, and then set this other mode. And every time we change between different modes, say like going between rendering text and rendering images, there's a cost that we pay, so we want to minimize those changes. And even within those modes, we want to make sure that we send big batches of stuff to render, because otherwise the GPU is not going to be using its full, it's not going to be used to its full potential. I could go on forever about this, but I only have 25 minutes, so I should really speed up and not get too sucked into the details of the GPU. Another thing that is a bit bad about this drawing model that we currently have is that sometimes we'll have also some effects that need to allocate a stacking context, so allocate an image, draw into it, and then apply some effect and draw that image into the rest. And for instance, if you have some transparency or some blur or something, that needs to be rendered that way. And that works fine as well for your CPU, because drawing into one thing and then drawing into another thing, like you're going to pay for a cache miss when you start drawing into that new thing, but it's still like it's a fairly okay price to pay. But for a GPU, switching between different render targets is really expensive. So this whole thing of going through the display list in order that is like back to front like this, and sending commands without doing some reordering and batching to minimize the number of state changes and random target changes is really, really expensive. And so any decent GPU backend to a painting abstraction like Canvas 2D or Skia actually do not draw every time you say, like, draw this rectangle. It won't actually draw that rectangle. It will record everything you ask it to do, and then it will wait as much as possible before it draws anything, so that it can look at the entire scene and go, okay, what can I reorder, what can I do to optimize this, so that we shuffle up that data in a way that is still correct, but fits the way we work with GPUs more efficiently. So what about WebRender? WebRender is it's a rendering engine that is that's been started by the research team, Mozilla, and now it's like the research team is still largely contributing most of the, say, optimizations to WebRender, but the graphics team is also, so my team normally works more on Gecko, is also contributing a lot of engineering effort into it these days. And so this is what I work on these days. It's a completely new rendering engine that doesn't try to use these abstractions that we use that look like Canvas 2D and that are sort of generic, and tries to think of how could we do CSS on the GPU and what's the shortest path between the two. So we have our display list, and display list is a pretty agnostic abstraction. It's like really CSS commands, and we have our GPU, and how do we design a new rendering system that maximizes the use of the GPU without like all of this fluff with the generic abstraction. So it's really designed for and around the GPU, and there is actually no CPU backend to WebRender. Means that if your GPU drivers are bad, you're not going to be using WebRender. You're still going to be using the other way we render things with Firefox, the current thing that I showed you before. because it's a completely new rendering engine, we can throw away our assumptions of what is fast and slow, and we can reconsider a lot of things that we've put into this really deep rendering pipeline, and that's kind of nice. And because we started from scratch, we wanted to do something that really tries to follow the same sort of tips and tricks that the games industry has been doing in the last few decades, and it's great because we have these GPUs that are built for video games, and we have a games industry that's been doing a lot of research into how to make rendering efficient, and a lot of these things are applicable to our 2D rendering problems, and it's great that we can use them because that way we don't need to reinvent the wheel all the time, and also we fall on some faster paths for the GPU. Like the GPU has been really optimized for the stuff that we're trying to do with it, as opposed to what we were doing before. And another nice thing with doing more things on the GPU is that we get more cycles on the CPU to do things like layout and JavaScript. So anything that we move from the CPU to the GPU is actually more responsiveness, more stuff that we can do on the other systems in the browser. So it's kind of nice actually. And thanks to Rust being an amazing language, we've been able to easily make use of more threads, and that works pretty well for performance as well. Or a rendering system before that is a threaded pipeline that doesn't have a lot of multi-threading, as in like fork join kind of parallelism. So with WebRender, we can do things like rendering glyphs in parallel, which we didn't do before, thanks to Rust. WebRender has been, so I was saying that WebRender is really trying to find the simplest way to render CSS on the GPU, and it sort of shows in the way it's been coded. Like this is one shader. I took this image from the test suite, and there's one shader program that can only do this and does exactly this. And what this is a border, a CSS border and the shader that runs like directly on the GPU. So like the really lowest level of abstraction can do things like groove and ridge effects. Like if I didn't know about this before, but like groove and ridge are like these sort of like effects that make it look like it's a bit bumpy. Can do dashing and can do border ready and stuff like that. So we actually hard-coded the CSS rules directly in the lowest level of the rendering engine, and just the fact that we were able to do this is actually amazing for me, because before we were going through all of these generic abstractions, and it was just not possible to like think about rendering CSS that close to the hardware. So it's pretty nice. Another thing that we do, and this sort of fits into this theme of doing what the games industry do, is Z-culling. And Z-culling is really something I'm excited about because it's very different from what we do currently, and to my knowledge, no other browsing engine actually do something like that. And I'm not even sure anybody else actually uses this technique to do 2D graphics. So what I'm referring to is that we use the GPU Z buffer to render things, and we render them front to back. So let me correct. Sorry, we render opaque primitives front to back. So if you have something with transparency, so say like a glyph, the glyphs are actually like text is rendered in the alpha path that is rendered later back to front. But we're able to render things front to back thanks to the fact that we can store in the Z buffer the something that corresponds to the Z index of the element we're drawing. So like it's like it's closer to you. There's this Z coordinate that is sort of arbitrary, but we use that to make sure that we first draw something that is the closest to you, and then when we draw something that's behind it, the GPU has like really hardwired capabilities that make it really fast to just not draw the pixels that are occluded by something that's already been drawn in front of it. And I don't know if it's something that we could easily do or that we could do it all on the CPU efficiently, but on the GPU, it's really burnt into the hardware, and it's really fast. And that saves us a whole lot of memory bandwidth. So in this diagram, what you see is like some really uninteresting page with only some rectangles and some numbers that are just like the Z index for each rectangle. And we draw things from front to back. So we first draw that pink little square there, and then stuff that was directly underneath, etc., until we get to the background. And that saves a lot of memory bandwidth. And today, memory bandwidth is really the most limiting factor in graphics in general, and in a lot of software. So saving bandwidth is awesome. And this is something that the games industry has been doing forever. Sorting opaque meshes front to back and rendering them like in that order is something that's been going on for like, I don't know, a decade or so. So it's really great that we're doing this, because this is one of the biggest optimizations that we got out of the WebRender in the last year. The other thing that's really interesting about WebRender is that now that we've been able to throw away our assumptions of what is fast and what is slow, we actually figured that we can render most things every frame. And we can actually do that roughly with the same speed as our naive compositor would, just like sample from that layer and render into the window. So without WebRender, we have this thing where we have a display list and we paint, and we run the content process. You saw that earlier. And then we have this complicated sharing system where we need to communicate through shared memory what we've painted, and then we need to composite. It means that if you're animating something like a border radius on a rectangle, even if the thing is going to change every frame, we have to render it into a layer before it reaches the screen. It's actually a little bit wasteful. And not only that, like this whole sharing system is actually doing some double buffering or triple buffering, depending on some configurations. And there's a lot of stuff that happens there, and we pay a cost for it. With WebRender, however, we just re-render everything. And if something is actually expensive to render every frame, we can always cache it. So we still have the benefits that we had with the layer system, where expensive things would be automatically cached in the layer system, because you can't really not cache anything. But with WebRender, we can just say, okay, these things like glyphs, like text is really, it's not very easy to do at 60 FPS if there's a lot of it. So it's a fairly good assumption that we should cache them, and so we do. We still do this optimization. But for the rest, like rendering a rectangle with solid color, it's a lot easier and it's a lot faster to just do that every frame than cache that into an image. When you go, if you like a lot of those websites are really simple, where you have like a lot of white background on each side and some text in the middle and maybe some images. If you look at the white background, most of it is actually painted into a texture and then later composited, and it's super wasteful. And seeing that actually, it drives me nuts. Like I really want to just say, hey GPU, just put some white into those pixels, or just clear the screen with the white color. There's even optimizations to clear screens faster. And don't try to like go through this like texture caching mechanism for things as simple as that. And it's the same for images. The image stays on the GPU, and then each image is kind of like a layer, if you will. So that's something that usually when I talk about this, people start freaking out and they say, what about my battery life? Like if you're rendering everything every frame, then maybe my battery is not going to be lasting that long. It's not actually that much of a concern, because for most web pages, really what WebRender does is as simple, or it's as fast and as efficient or more efficient than what the compositor would do. Thanks in part to this Z-culling thing, because memory bandwidth is pretty expensive for battery life as well, and Z-culling really reduces that. So we don't have too much overdraw, and that makes things fast. And another thing that people ask a lot, so I'm going to dispel this here, we render everything every frame, but if nothing's changed, we're not going to re-render, we're not going to refresh the screen if nothing's changed, right? Like, so if you're sitting next to a website and nothing's been moving, we won't wake up your GPU. But if you're scrolling, then when things change on your window, we need to re-render things. I don't know how much time I have left. I've already probably been 5 to 10 minutes. Okay, well, because I can skip that part if you want to move on. But yeah. Okay, cool. Sorry about that. So in Firefox, because I've been talking about WebRender, I'm pretty excited about this. But going from hey, we have this really great rendering engine to hey, we have Firefox that uses that great rendering engine is like a lot of work. Like, a lot more work actually than doing the rendering engine itself. So the way we go about this is that Firefox has its own display list representation, the one I showed you earlier, and WebRender has a display list of its own, and it's pretty much its API surface. And in Firefox, what we do is that we've set up the thing so that we can have a channel that sends display lists to WebRender and make it so that we can give it GL context that you can draw into and things like that. So we've done this plumbing, and now a lot of the work is making sure that we can translate our own display items into WebRender display items. And a lot of time they don't actually match, so it's actually a subtle sort of thing to do. And a lot of the remaining work has also been looking at WebRender and saying, okay, so WebRender doesn't yet support this like corner case of how we render text with like I don't even know the word in English, but like complicated corner cases, and the web is just full of them, and so we go through them and we add those features. So it's actually great for Servo because they get a lot of new features for free because we need them in Firefox. Like the first thing I did in WebRender was adding a shader that can decode YCBCR images, because this is the format that video frames are sent or are decoded into, usually. And so now WebRender can just take video frames and render them, and you couldn't do that before. So a lot of the work that's going on right now is really making sure that we properly send a display list to WebRender that matches the display list that we build in Gecko as a result of the layout. And that's quite a bit of work. And I know that the first question people are going to ask me is, when can I use WebRender? So I'm going to answer that now. I have no idea. Well, actually I do, but I'm really afraid of telling you a date and then people like calling me up on that. So I'm gonna pretend I don't know, but it's in a little while. Like the state of the integration is still pretty rough. There's still a lot to do. But you can try it out. You can take your nightly build of Firefox, which I'm sure you all use, so it's great, and you can fiddle with the preferences and enable WebRender in Firefox. And it's probably going to crash. For some things, it's probably going to be a lot faster. For some things, it's probably going to be a lot slower. Because one thing that I didn't say before is also that like there's a bunch of stuff that WebRender doesn't support, like SVGs now in the roadmap in the short term. And so we still use Gecko's rendering engine for these things. So we have this hybrid setup where like if something is not doable with WebRender, we just do it on Gecko's side and then we pass it to WebRender as an image. But as we're going through display items, there's still a lot of display items that we should be rendering with WebRender. But instead we do them on the Gecko side, and that's like pretty slow. So don't freak out if WebRender makes your Firefox really slow right now, because this is not representative of the final product. If you want to follow the development, there's a newsletter that I write at the graphics team's blog. On hacks.mozilla.org, there's a really brilliant blog post by Link Park that explains what WebRender is and why it is. If you haven't read it, it's really great. And also find WebRender in GitHub and read the code, learn from it, send us pull requests, and become a hero. Thank you very much. This is the end of